Welcome to the deep dive. Today we're getting into something really core to making AI work better in the real world, making these super powerful reasoning models, the brains behind things like OpenAI's models or DeepSeek R1, not just smart, but fast too.
Right. Because these models, they can do incredible deep thinking, really tackle complex problems with human-like accuracy. It's impressive stuff.
It really is. But that deep thinking, it costs a lot.
It does, both in terms of time latency and the sheer amount of computation needed. It's because their process is quite intricate. They explore options, double-check, backtrack.
Which is great for hard problems. But here's the thing we're looking at. Even for simple stuff, they often go through that whole rigmarole.
Yeah, which leads to delays and, frankly, wasted resources. It's overkill.
Exactly. It's like using a supercomputer to calculate a tip. It feels slow and inefficient when you just want a quick answer.
And that creates a suboptimal user experience, especially when speed matters.
So the big question, the one this paper tackles, is can we have it both ways? Can we keep that amazing reasoning for the tough challenges, but get quick, efficient answers for the easy ones?
That's the core challenge. And it brings us to this paper from Tsinghua University. AdaptThink. Reasoning models can learn when to think. The authors are Jiaji Zhang, Niani Lin, Lei Hu, Ling Feng, and Wanzi Li.
So our mission today is to unpack AdaptThink. We want to understand their approach and figure out what it means for the future of AI, this balancing act between thinking deeply and responding quickly.
Okay, let's dig in. To really appreciate AdaptThink, you first need to grasp why these models tend to overthink.
Right. What is that standard thinking process they usually follow?
Well, the paper describes it as pretty thorough. They explore different potential paths to a solution. They reflect, kind of ask themselves, am I on the right track? Right. They might backtrack if they hit a dead end, try a different approach. And then crucially, they do a rigorous self-verification before actually giving you the final answer.
And that whole process, while powerful, is what leads to those high costs you mentioned, the computation and the waiting time.
Exactly. That's the inference cost and latency the paper talks about, referencing some recent studies. It all adds up.
And other research confirms this isn't great for users asking simple questions. You ask something straightforward, wait several seconds, maybe get pages of internal thought logged. It just feels clunky.
You're left wondering, did it really need all that? It breaks the flow.
Now, people have tried to fix this before, right? The paper mentions some earlier efforts.
Yes, there's been work on just reducing the length of the final response, using things like reinforcement learning with rewards for brevity, or fine-tuning with pairs of responses where one is preferred for being shorter, even merging smaller models.
But the key difference here, the insight-driving AdaptThink, is that those methods still make the model think every single time?
Pretty much, yes. They might trim the output, but the underlying, often lengthy reasoning process is still applied universally, even when it's not necessary at all for that specific problem.
Okay, so that sets the stage for this idea of no thinking. That sounds counterintuitive for a reasoning model.
It does a bit. But researchers started experimenting with just prompting models to, skip the thinking part and generate the solution directly.
How did the AdaptThink authors approach this not thinking?
They used a really simple technique. They basically give the model an empty thinking segment in the prompt. Just think.
Huh. So it's like saying, okay, have a think. Just kidding, give me the answer.
That's a pretty good way to put it. And they did some pilot tests using a math data set, Match 500.
And what did they find?
This is where it gets really interesting. For the relatively simpler problems, sort of up to high school competition level math, this not thinking approach actually achieved comparable, sometimes even better accuracy than the full thinking process.
Wow, better accuracy by not thinking.
It seems counterintuitive, but yes, for some problems. And the big win, of course, was that it drastically reduced the number of tokens generated the response length.
So the heavy-duty thinking really only pays off for the genuinely hard problems.
That seems to be the key takeaway. For easier stuff, it's often just adding computational overhead without improving the final result.
The paper has a figure 2, that shows this, right? Comparing thinking versus no thinking.
Yes, it compares accuracy and response length for a specific model across 5 difficulty levels on Math 500. You can clearly see on the easier levels, accuracy is neck and neck. Sometimes no thinking edges ahead slightly, but the response length for no thinking is way, way shorter.
Dramatically shorter.
Exactly. And they also looked at individual problems. They found that for levels 1 through 4, thinking only actually helped get the right answer less than half the time compared to just going straight to no thinking.
Okay, so all this leads directly to the core idea behind AdaptThink. Can we make the model smart enough to choose?
Precisely. Can the model learn to adaptively pick between thinking and no thinking based on how difficult the problem seems, so we get efficiency without losing performance on hard tasks?
And AdaptThink is their answer, a new reinforcement learning algorithm designed specifically for this.
That's right. It's built to teach these models when it's worthwhile to engage in that deep thinking, and when the quick no thinking route is better.
So how does it work? The paper mentions two main components. Let's start with the constrained optimization objective. Sounds technical, but what's the goal?
The basic idea is simple. Push the model to use no thinking more often, because that's where the efficiency gains are. But, and this is the crucial constraint, don't let the overall accuracy drop.
Right. Efficiency, but not at the cost of performance. How do they formalize that?
They set it up mathematically in equation 2. It aims to maximize the chance of choosing no thinking, while ensuring the model's accuracy stays at least as good as a baseline, what they call a reference model, basically, the model before AdaptThink training.
And making that constraint practical for training involves turning it into a penalty.
Exactly. Equation 3 shows this. If the accuracy dips below the reference model's level, a penalty kicks in. There's a weight, lambda, that controls how strong that penalty is. Then some algebraic shuffling gives them equation 4, which is a bit easier to work with.
But how do they know the reference model's performance during training? They can't keep running the old model constantly.
Good question. They approximate it. Before training starts, they collect a set number of answers, K, from the original reference model for each training problem. They calculate the average accuracy from those answers.
Okay, so they establish a fixed benchmark beforehand.
Right. And that benchmark is used in the final optimization objective, which is equation 6.
So the goal is set, but learning this involves reinforcement learning, policy gradients. How does that work with binary outcomes like correct, incorrect, or thinking, no thinking?
They use a policy gradient method, specifically a variation of PPO that's proximal policy optimization. It's laid out in equation 7. They actually omit a common part, the KL penalty, finding it wasn't needed here. They define an advantage function that rewards choosing no thinking unless doing so hurts accuracy significantly below that reference benchmark, incorporating the penalty.
And there's clipping involved too.
Yes, that's a standard technique in PPO to keep the updates stable during training, preventing the policy from changing too drastically in one go.
Okay, so that's the objective, what the model should learn. But then there's the second piece, important sampling strategy. What problem is this solving?
This tackles what they call the cold start problem. Imagine you have a model that has only ever been trained to think. It's just not going to spontaneously try no thinking.
So it wouldn't get any examples of no thinking to learn from in the early stages of RL training?
Precisely. It's stuck. So important sampling, defined in equation 8, is their way around this. It deliberately forces the model, right from the beginning of training, to try both modes.
How does it force it?
They set it up so that for the very first token the model generates, there's roughly a 50-50 chance it will be the start of a no-thinking response, like the think tag, or the start of a typical thinking response, like a common starting word. They mention all right as an example.
So it guarantees exposure to both strategies right from the start.
Exactly. This ensures the model gathers data on the outcomes of both thinking and no thinking immediately, allowing the reinforcement learning process to actually compare them and learn which is better in which situation.
And this isn't just for the very beginning?
No, the final loss function they use, LAT, in equation 9, incorporates this important sampling throughout training. It ensures continued exploration of both modes, preventing the model from just defaulting to one strategy once it starts learning. It maintains a balance between exploiting what works and exploring alternatives.
That's quite clever. It makes sure it actually learns the trade-off. The paper also offers another way to look at this learning process using average advantages.
Yes, they define the average advantage for thinking and no thinking in equation 10. For thinking, it's basically how much better its accuracy is compared to the reference model.
Okay.
For no thinking, the advantage calculation also includes that penalty factor, delta, we talked about, effectively rewarding it for being efficient, plus its accuracy difference compared to the reference.
And this helps explain when the training pushes towards no thinking.
Exactly. Equation 11 shows the condition. The training process favors no thinking if its average advantage is positive and higher than the average advantage of thinking. This generally happens when the accuracy drop from using no thinking, compared to both thinking and the reference model, is less than that d value.
So if notthinking is almost as accurate, or the problem is easy enough that accuracy isn't hurt much and it's faster, implicitly rewarded by the objective, the model learns to prefer it.
That's the idea. But for harder problems where no thinking performs much worse, its advantage drops, and the learning process prioritizes accuracy, pushing the model back towards thinking.
It really ties back nicely to that difficulty adaptive goal. Okay, theory sounds good. How did they test it? What were the experiments?
They used two main base models, derived from DeepSeek R1 but distilled into Qwen architectures, a 1.5 billion parameter version and a 7 billion parameter one.
And the training ground.
They used a dataset called DeepScaler, which has about 40,000 math problems. Math is convenient for RL because checking the answer correctness is straightforward.
Makes sense. And for evaluation, seeing how well it learned.
They used three math datasets with increasing difficulty. First, GSM-8K, that's grade school math. Then MAT 500 high school competition level. And finally, AIM 2024, really tough problems from the American Invitational Mathematics Examination.
And they measured.
Primarily accuracy and response length, which are the core metrics here. They also calculated the average accuracy change and the average reduction in response length across those data sets.
Did they mention anything about the setup, like context size?
Yeah, they used a 16K context size and a temperature of 0.6 for generation. For AIM, since it's small, they ran tests multiple times and averaged the results for reliability.
Any specifics on the training itself, like how long it took?
They used a framework called VRL. They mentioned details like training context size, batch size, learning rate, and the specific values they chose for those key hyperparameters like K and DI. They also noted the training time and hardware a few days on multiple A100 GPUs for the 7B model, less for the 1.5B. And they picked specific training checkpoints for the final evaluation based on performance.
Crucially, how did AdaptThink stack up against other methods trying to do similar things?
They compared it against a whole suite of baselines. DPO shortest, Overthink, DAST, O1 pruner, Teal Amory, model merging, and RFT mixed thinking. And importantly, they reran all these baselines themselves on the same DeepScaler training data for a truly fair comparison.
Okay, the moment of truth. What were the main results? Did it work?
The results in Table 1 are pretty striking. For the 1.5B model, AdaptThink reduced the average response length by 53%. For the 7B model, it was a 40.1% reduction.
Wow, that's a huge efficiency gain. What about accuracy? Did it drop?
That's the amazing part. No, accuracy actually improved on average by 2.4% for the 1.5B model and 2.3% for the 7B model across the evaluation datasets.
Getting shorter responses and better accuracy? That's the dream scenario.
It really is. And it outperformed most of the baselines on both fronts, achieving the best average results overall. It strongly suggests this adaptive approach is really powerful.
Table 1 also had that Roche and team metric, the percentage of times it chose notthinking. What did that show?
That clearly demonstrated the adaptive behavior. On the easier datasets, GSM-8K and Math 500, AdaptThink used notthinking much more often. But on the really hard AIM problems, it shifted gears and used thinking much more frequently.
So it learned to recognize difficulty and adjust its strategy.
Exactly. And figures 3 and 5 break this down even further within the Math 500 datasets difficulty levels. You see a clear trend, mostly no thinking for level 1, gradually increasing the use of thinking as problems get harder up to level 5.
And accuracy stayed strong throughout this adaptation.
Yes, AdaptThink generally maintained higher accuracy compared to the original models that were stuck using only thinking or only no thinking.
Very convincing. They also dug deeper into how it works, right? Like the effect of that delta parameter.
Right. Table 2 looks at this for the 1.5B model. As they increased delta, basically, telling the model to prioritize efficiency more, it produced more not thinking responses and shorter lengths, as you'd expect.
But what happened to the accuracy gains?
They gradually decreased a bit as delta went up. So delta really acts like a tuning knob. You can use it to control that trade-off between efficiency and maximum accuracy improvement.
Makes sense. A higher delta means push harder for speed, potentially sacrificing a tiny bit of the accuracy boost.
Exactly. But what's interesting is even with delta set to 0, meaning no explicit reward for efficiency beyond not hurting accuracy, the model still chose no thinking over 50% of the time on easier problems.
Suggesting there's maybe an inherent benefit to no thinking for those simple cases, even beyond just speed.
It could be. Perhaps it avoids getting tangled in unnecessary reasoning steps that might lead it astray on simple problems. The main point, though, was AdaptThink's robustness. It worked well across various delta values.
And what about the importance sampling? How crucial was that specific technique?
They compared AdaptThink directly against a version without importance sampling, which they called naive GRPO. Figure 4 shows the training curves.
That's the difference.
GRPO, sampling directly from the model's current policy, struggles initially because the model starts out mostly thinking. It learns to improve accuracy in thinking mode, but it barely explores no thinking. So the response length reduction is minimal and can even reverse later in training.
Whereas AdaptThink, thanks to important sampling, forcing it to try both modes from the start, learns the benefits of no thinking for simpler tasks much earlier, and achieves that significant sustained reduction in response length while also improving accuracy. So that sampling strategy is really key to enabling the adaptive learning.
Absolutely. It kickstarts and sustains the exploration needed to learn the efficiency trade-off.
Okay, another concern they looked into was the model cheating. Was it sneaking thinking steps into its no-thinking responses?
Yeah, they call this implicit thinking. They checked for keywords associated with reasoning, like wait, alternatively, in the no-thinking outputs from AdaptThink, and compared the frequency and length to the original thinking and no-thinking modes.
What did Table 3 show?
For the 7B model, there was only a very slight increase in these implicit thinking markers and a tiny increase in the average length of the no-thinking solutions generated by AdaptThink. It wasn't a major issue.
And they had an idea to fix even that small increase.
Yeah, they suggested potentially adding a penalty during RL training if implicit thinking is detected in a no-thinking response. Give it 0 reward, perhaps.
Good foresight. What about generalization? Did AdaptThink only learn this trick for math problems, or could it apply it elsewhere?
That's a critical question. They tested it on the MMLU dataset, completely different domains, question formats, everything, out of distribution testing.
And the results? Table 4.
Pretty positive. AdaptThink still cut the average response length by over 30% on MMLU. It achieved this by using no thinking for about 16% of the problems.
Yeah.
And interestingly, it also scored higher accuracy on MMLU than the original baseline models.
That's really strong evidence for generalizability. It learned a principle, not just a dataset-specific trick.
It seems so. And they included case studies, figures 6 through 9, which really illustrate this.
What do they show?
Figures 6, 7, and 8 show examples from GSMA-K, MAT 500, and MMLU, where AdaptThink, the 7B version, correctly uses the short, direct, no-thinking approach for relatively simple problems. And they contrast it with the original model's much longer, more complex thinking trace for the exact same problem.
You can really see the difference.
Definitely. And then figure 9 shows the flip side. A challenging AIM problem, where AdaptThink correctly identifies the difficulty and engages the full necessary thinking process to get the right answer.
It visually confirms that adaptive selection process.
Okay, so it sounds very promising, but like all research, it has limitations. What did the authors acknowledge? The main ones were computational constraints. They only tested up to 7 billion parameter models. They'd like to see how this scales to even larger models.
Makes sense.
And also the training data. It was heavily math-focused because answer verification is easy there. While the MMLU results showed good generalization, they suggest that training on more diverse data types could potentially make AdaptThink even more robust across different domains.
Understandable limitations. So let's wrap this up. What's the big picture here? The main takeaway from this deep dive into AdaptThink?
I think the core message is that AdaptThink presents a really compelling approach to making powerful AI models more practical. By teaching them when to think deeply versus when to be quick and direct, it tackles that efficiency-accuracy trade-off head-on.
And it shows you can get significant efficiency, gain shorter responses, less compute without sacrificing accuracy, and sometimes even boosting it.
Exactly. It's about adaptive intelligence. The model learns to manage its own reasoning resources based on the task's demands. That's a big step towards more versatile and user-friendly AI.
You can really see how that improves the interaction. Quick answers for simple things, deep thought when needed. It makes the AI feel much more responsive and less like a black box churning away unnecessarily.
Precisely. And looking ahead, this kind of adaptive computation, where the AI system intelligently allocates its resources, could be fundamental as AI gets embedded into more complex, real-time applications that handle a huge variety of tasks.
Which brings us to a final thought for you, our listener. We've seen how AdaptThink works for mathematical reasoning, but how might this core idea, learning when to engage different levels of processing, apply elsewhere in AI? Could natural language models learn when a deep semantic analysis is needed versus a quick keyword check?
Or maybe creative AI tools, learning when to iterate extensively versus generating something directly. What new challenges pop up when you try to define thinking versus not thinking in domains like language or art, where correctness isn't as clear-cut as a math problem?
It definitely opens up some fascinating avenues for future research and development. Something to ponder. Thanks for joining us for this deep dive.